In this video, we're going to look at problem 2 from the separate LO1 tutorial questions, which you'll find on the My City page. In a problem like this, we're given the loads that apply to the beam and information about what kind of support we have, but we're not told what the reactive forces or moments are going to be. But we're given a clue. If we look at the beam here, we'll see it's supported at only one point, this right-hand side, and this is simple support that's going to provide reactive forces to any horizontal or vertical forces and to any moments that are applied relative to this point. So we'll label this point A so we can get an understanding of what's going on here. And we'll imagine that, that there could be vertical reactive forces, which I'll call VA, could be called RA, just depending on its names. There could be horizontal reactive forces, HA, and there could be a moment, and we'll find out that actually are some of the things. And I've just drawn in, just to show it's a turning, we determine the direction of the moment when we do our calculations. I think the first things first to say that HA is going to be 0. There are no horizontal forces in this particular problem, so we don't need to deal with that. We do need to think about VA, because we know there's vertical forces. We can see on the diagram that there's 2 point forces applied acting vertically downwards. There's only 1 point VA where there can be a reaction, and we know that because we have static equilibrium, these must sum to 0. So the sum, sigma, of all the vertical forces is 0, which means 10 plus 15 are 2 downward forces minus VA, or upward force. In fact, I should do that with the correct directions. VA is acting up, that's positive. Minus 10 minus 15 is going to be equal to 0. So we only have one vertical reactive force, that must be equal to the sum of all downward vertical forces. So listen, VA is 25 kilonewtons. And at this point, we actually have all the information we need to do our shear force diagram, because that's all shear forces identified. But before we do that, we'll go and look at the moment. Now, similarly, we have the moment is equal to 0 at all points in this diagram, which means any moment, any turning action due to these forces must be counterbalanced by a moment at MA. And what we find here is that if we look at what the bending moment is at point A, we look to the left, because everything here is to the left of A anyway, and we see we're going to have minus 10, because it's acting in the counterclockwise direction, times 5, that's 5 meters away from A, and minus 15 for the second point force multiplied by 3. That's going to give us minus 50 minus 45 for our bending moment at point A to be a total of minus 95 kilonewton meters. To have all of the information for our bending moment diagram, we need to know all the bending moments in this diagram. So we'll label these points B and C just now, just for reference. The bending moment at point B, you might have guessed, but there's nothing happening to the left of B. There's no support there to provide moment, so that's going to be 0 kilonewton meters. And at point C, we only consider the force to the left of C, which is at point B, and that's acting in the counterclockwise direction at a distance of 2 meters away. So that gives us minus 20 kilonewton meters. So now we have all of our information, we can begin to make our diagrams. So let's have a look at a shear force diagram now. I won't bother with the ruler, I'll just do this a bit roughly. Take a nice line here for our diagram to begin. So this is our baseline of zero shear force. I'll mark these zeros here. Now what's happening as we move across our beam? Well, if we start on the left-hand side at point B, immediately we have a downwards shear force of value 10. So I'll draw it down here. So this is taking us to minus 10 on our shear force diagram. Now, we know from other problems that we're going to move across horizontally because there's no force being applied between points B and C. So we move horizontally across to where point C is, and then it's another force of minus 15 applied. So we go down a further 15, and that takes us to minus 25 in terms of shear force. Again, there's no forces applied until we reach point A, our support, so we go across, and of course we know from our calculation up here at the top, this is what's going to take us back to 0. We have 25 kilonewtons positive shear force acting up the way, so that completes our shear force diagram. And if you look at the solutions to the problem that you find on MyCity, you'll see a very similar but more neatly drawn diagram than that. So I've just erased the shear force diagram so we can create our bending moment diagram just now. So similarly, I'll draw a straight line across the page to represent 0 bending moment. Well, straight enough line. Now we've worked out the bending moment at points A, B, and C. So starting from left to right, at point B, we have a bending moment of 0, which I'll mark on here. At point C, we've got a bending moment of minus 20. Remember, negative bending moment we plot above the line. So we'll call this negative 20 at point C. And then we calculate the bending moment of negative 95 at point A, where the support is. So just mark these at minus 20, minus 95. And if you remember, when we have straight horizontal lines between our forces on the shear force diagram, these should be straight lines. I'm going to draw now. We have straight lines at an angle between points. That's meant to be a straight line, and as is this meant to be. Well, excuse the interruption there. We lost a few seconds while the computer had a little hiccup. So I will now draw the final part of the bending moment diagram. That's meant to be a straight line there as well. And you can see we don't return to 0 because at the right hand side the bending moment isn't 0, so that's what our diagram should look like. And again, you'll find a neater version of that in the solutions on the MyCity page.